So let's talk about a topic that everybody really enjoys, salmonella. So I have decided to go to the store and I'm going to purchase some chicken and I'm going to test that chicken for salmonella. And what I'm guessing is that if you buy a name brand type of chicken, that is probably taken care of a lot better than, say, a store brand. So for example, if I go buy Tyson's chicken breasts, I expect that that will be a somewhat cleaner product than if I went and bought like Hill Country Fair Chunks O chicken. So what I'm going to do is I'm going to go to the store. I'm going to buy a whole bunch of chicken. I've been given a very large chicken-related grant to go do chicken research. And what I want to know is the name brand chicken safer than the non-name brand chicken? So let's assume I'm going to compare Tyson chicken and I'm going to compare Sam's Choice chicken. Okay, so I've got the name brand chicken, Tyson, the king of chicken, and Sam's Choice, the cheap chicken, and we're going to see if one is more or less likely to be contaminated. So I'm going to make sure I do this experiment right, and I'm going to go buy 75 packages of each. So I get 75 packages of Tyson and 75 packages of Sam's Choice. I'm really in the mood for chicken, so I go buy 150 total packages of chicken, and I check them. And in this Tyson package, my name brand chicken, I find out that 33% of these packages, which is 25 of them, contaminated. And in my Sam's Choice, let's say 45% of my chicken is contaminated. And what I want to know is the store brand more contaminated than the name brand? So is the store brand, Sam's Choice in this case, more contaminated than the name brand? It certainly looks like it. It's about 12% higher right now, but 12% might not be significant. We'll have to check and see. So let's assume, me being a good statistician, that I met the conditions for success and failure. Of course, 25 is 33% of 75. That'd be 25 packages, so I have at least 10 successes. Success in this case being salmonella, which I believe that's everybody's definition of success, is having salmonella. So 25 have salmonella, which means 50 don't. So I got at least 10 successes and failures there. Over here, 45% of 75. I don't know exactly what that number is, but I know it's more than 10. This is almost half of the 75. So we'll say 30 to 35 successes and a few more failures. So I meet that condition. We'll assume I picked the chicken at random, and we'll also assume, now this is important, that whenever I got the chicken, that I went to multiple stores or bought it at multiple times, because if I got all the chicken at the same time from the same store, they probably wouldn't be independent, because if one batch of chicken was bad, it might affect every other piece of chicken in that batch. So we'll assume I was a good statistician and that I met all of the conditions for normal distribution. So let's write our hypotheses here, and of course my null hypothesis is that they're the same, right? Your null hypothesis is there is no difference in contamination between the two. So I could write this in two different ways. I could say, well, the percentage of contamination in the store brand is equal to the percentage of contamination in the name brand, which could also be written as the store minus the name brand is 0. I could also, let's see, do the alternative hypothesis. And the alternative hypothesis is going to be that the store brand, Sam's Choice, is worse than the name brand. So the proportion of contaminants in the store brand is more than the contaminant in the name brand, or alternatively that the store brand minus the name brand is greater than 0. The difference between the two is greater than 0. Store brand's more contaminated. I'm assuming that because when I picked up my chicken, turns out store brand actually does seem to be quite a bit more contaminated, 12% more contaminated. Of course, the most horrifying thing is best case scenario, I'm looking at 1/3 of my chicken being contaminated with salmonella, but that's a discussion for another time. So assume I've met all of the conditions, and remember I have to check the conditions for both groups, enough successes and failures for both. They both have to be independent. They both have to be random. I'm making kind of a leap, assuming that they're independent. I am assuming that I am a good statistician and that I did not buy them all from the same load of chicken. So assuming that is true, I meet the conditions. So let's go ahead and use the normal model, and what we're going to do is a 2 proportion z-test. And we're doing a 2 proportion z-test because I will be using z-scores to get my answer, and I'm comparing two proportions. So let's go ahead and get the mechanics out of the way here. In my store brand group, I told you that I had 75 total packages, and that of those 75, 45% were contaminated. Now it turns out my 45% was sort of a stupid number for me to pick. I did this for 34%, and so the proportion is about 45%. It's not exactly 45, it's actually 45.3, but bear with me. 34 out of 75 is about 45% contamination. And then my name brand, my Tyson chicken chunks, that was 33%. That's assuming that there were 25 packages. Successful packages, successful meaning totally contaminated. That's about 33%, which means the difference in the two proportions, the proportion of, let's do proportion of the store brand minus the proportion of the name brand, is going to be about 12%. Nice. The difference between them is 12%. Now, I know in a minute I'm going to do a hypothesis test, which means I'm going to want the numbers to be pooled. So let's just go ahead and do that. Let's go ahead and figure out what it would be pooled. Remember, pooled is what I do with the numbers to show that I believe the null hypothesis, that there is no difference between the two. So I add the proportions together and get one lump proportion for the whole group, in this case 0.393. So I'm saying that I believe overall it's a 39.3% rate of contamination, which is horrifying that 39% of chicken is contaminated. Pretty awful. Let's go ahead and do a z-score. The difference between the two is actually 12%. We just figured that out. And if our null hypothesis is true, the difference between them should have been none. There should have been no difference. Standard deviation on the bottom. So remember, I'm assuming a 0.393 rate of success, which means a 0.607 rate of failure. And the first group had 75. The second group, 0.393, 0.607, that group also had 75. And so whenever I figure out the z-score here, I get 1.50. 1.50 is the z-score for that gargantuan problem here. And remember, my alternative hypothesis was greater than 0 was the difference. So whenever I go look this up on my z-chart, I'm looking to find the probability that z is greater than 1.50. Okay, so I go look that up. Let's go ahead and do my normal model here. There's 0 standard deviations. Here's 1.5 standard deviations. And I'm looking for greater than. It turns out the probability of this happening is 0.066. So my p-value is 0.066, or 6.6% if you like. 6.6%. So this seems like it's kind of a low p-value. I don't know that it's crazy low. It sort of depends on what I picked for my alpha value. If I picked, let's say 5% for my alpha value, then this is okay. It seems like this is fine. If I picked 10% for my alpha value, this seems like it's below the alpha value of 10%. So this completely depends on what I chose for my alpha value. Now, we always have been choosing 5% for our alpha value, and I didn't say any differently this time. So let's go ahead and assume that we were still using an alpha value of 10%. Remember, unless the problem specifically says, it's a safe bet that alpha is going to be 10%. So we're going to say, because the p-value is above our alpha of 5%, we fail to reject the null hypothesis. There is no evidence the store brand is more contaminated than the name brand. Now this is one of those cases where the alpha value you pick determines or is determined by whether or not you consider a type 1 or a type 2 error to be worse. In this particular case, a type 1 error would mean that there is no difference between the two, but I think that there is. I think one is worse than the other, even though there's not. And a type 2 error would mean they are different. One is worse than the other, but I think everything's fine. I would argue that I think a type 2 error is maybe worse to make than a type 1 error. Because in a type 1 error, I throw away chicken that is perfectly good. I say, oh no, it's contaminated, let's throw it out, but it turns out the chicken was fine. Contrast that with, I think the chicken's fine, I don't know what you people are talking about. No, I have no idea why everybody's throwing up and dying from salmonella. This is type 2 is maybe a worse error to make. So I am okay with making a type 1 error, or I should say I'm more okay with making a type 1 error than I am with a type 2 error. A type 2 error would be worse. And in order to decrease the chance of making a type 2 error, I might choose a larger alpha value. Now we used 5% here, but we were at a p-value of 6.6%. We were knocking on the door of that alpha value. We were pretty close to our alpha value 5% already, and if I'd done a 10% alpha value, then I would have rejected the null hypothesis. And in this case, if you were allowed to choose, you might go for a higher alpha value of 10% just because a type 2 error would be so much worse to make than a type 1 in this case. So I solved the problem as though we were doing an alpha of 5%, but it would be completely reasonable of you to do an alpha value of 10%, which means you would reject the null hypothesis. Okay, I think that is perfectly legitimate if you chose a different alpha value. So last thing, let's make a confidence interval. So let's do a 90% confidence this time. We always do 95. Let's try something different. So the difference between the two was 12%, and it'll be plus or minus, and a 90% confidence interval will be 1.645 times the standard deviation. Remember, in a confidence interval, we use what actually happened. Whenever we're working this out. It's the amount of contamination we actually got. So the first one had a 45.3% contamination rate, which means a 54.7% failure. Failure in this case means you did not get salmonella. That's a weird definition of failure. And group number 2, 33% and 67% out of 75. Okay, so here's what it'll look like. There's group number 1 and there's group number 2. The 75s are the same because the groups were the same size. If I'd only gotten like 60 of, I forgot which one this was, 60 of store brand and like 90 of name brand, then these numbers would be different. They're just the same because the groups happen to be the same size. Anyway, you can work this out on the calculator. I worked it out beforehand so you wouldn't have to watch me punch on the calculator, and it turns out that that's what the rate is. So I would say I'm 90% confident that, and what I'm talking about is the difference. The difference is between 9 and 35%. So I'm saying I'm 90% confident that the rate of contamination in, what do we call it, Sam's Club? Or Sam's Choice? The rate of contamination in the Sam's Choice chicken is 9.7% to 35.7% higher than Tyson. Now that right there is pretty telling. It's pretty telling that I'm 90% confident that best case scenario, Sam's Choice, is 9.7% more contaminated. Now, our hypothesis test, we said we failed to reject the null hypothesis because we were above alpha. But then we go to the confidence interval and we say, oh my God, even the best case scenario, it's 9% more contaminated. Maybe this alpha value was too low. Maybe we should have gone with 10% because our confidence interval indicates that it is more contaminated all the time. I'm 90% sure that the true proportion of contamination Sam's Choice has above that of Tyson is between 9 and 35%. This is contaminated chicken right here. This is not good that Sam's Choice is between 9 and 35% more contaminated. So that might be an indication that maybe 5% was too low of an alpha value, and maybe I should have gone with 10% instead. 10% would reject the null instead of fail to reject, which would make me think Sam's choice was more contaminated, which does seem to line up with what my confidence interval says. Again, alpha is usually up to you. You're usually allowed to pick your alpha unless the problem specifically says use an alpha value. You're allowed to pick what you want. But you want to pick an alpha value that makes sense with your types of errors. In this case, a type 2 error I think would be much more of a catastrophe than a type 1 error. So I might want to raise alpha to decrease the chance of making a type 2 error. It will increase the chance of making a type 1 error, but a type 1 error I think would be much less awful in this case than dealing with a type 2 error. So be careful when you pick those alpha values. It can have a really big difference in the outcome of your hypothesis test or confidence interval.